So, the actual subject for today is to get us started talking about one of these fundamental problems in networking, which Sylvia mentioned, which is routing. So sort of, setting the scene, the game plan for today. We'll see how this actually works. I'm going to start out sort of setting the scene with a quick disclaimer, a quick statement on addresses. Then I'll talk a little bit about what is a router. I'll talk a little bit about, why we have routers at all. I'm going to then sort of present like the challenge of routing and then the challenge of forwarding. Then I'm going to sort of compare and contrast the two of those. Then going to get a little bit into theory. We're going to talk about sort of a graph representation of routing. We're going to talk about this notion of routing validity, and then we will see how to actually use that notion of validity to validate routing state. And then we will probably end up with this in-class activity. So the disclaimer here is that there are about 1 billion ways to do routing. And I'm going to sort of constrain our initial discussion today to sort of like how the archetypal internet works. I'm going to make a lot of assumptions based on this. And next week we'll talk about some alternatives. So if you cast your mind back to the salad days of 2 weeks ago, we talked about packet headers. And we said that a packet header must contain a specific field. Does anyone remember what field we said packet header must contain? Yeah. The destination IP, or more generally a destination address. And so I think one can actually argue that you could build a network where this isn't true, but it's true for like every networking technology I could easily think of, and it's certainly true of the internet. And I'm not sure that we've outright stated this before, but this sort of implies that hosts have addresses. Thinking back to Sylvia's example with CEOs delivering letters, the CEOs had some address associated with them, like one infinite loop in Cupertino for Tim Cook, or one Hacker Way in Menlo Park for Mark Zuckerberg. And in fact, hosts might have more than one address. So why is that? Why might a host have more than one address? Yeah. What was the second part? Yeah. So anybody else have another reason? Yeah.
They have multiple servers, such as they need multiple addresses.
Multiple servers?
Yeah, multiple servers, like one in different locations to help people get better performance and stuff.
So I think you're onto something, though I might say it a little bit differently. And so the sort of two reasons, I think, if I'm interpreting kind of what you're getting at correctly. So one of them was that you might have different addresses for different layers, right? Like, your cell phone, right? Or just, any computer, might have like an Ethernet address, an L2 local address, and it might have an L3 IP address, a global address. So it might have, addresses at different layers. The other one is, I think, what we were getting at over here, which is you might be connected to multiple networks, and you might have a different address on both of those networks. For example, your phone, you might be connected by Wi-Fi and by cellular, and each of those connections might have a different address. So for now, though, and for much of our discussion on routing, we'll be thinking a little bit more abstractly. So we'll just think of a host as having, a single sort of abstract address. We'll get into some sort of technical details of addressing next week. But for now, I'll probably draw hosts something like this, and say that a host drawn like this has the address F. So, moving on, let's ask a pretty basic question, which is, what is a router? There's a bunch of different ways to answer this question. Again, casting our minds back to lecture 1, we had a diagram that looked something like this. And it had this thing labeled switch on it. As Sylvia has talked about, when she and I say switch, we often mean that kind of interchangeably with router. And so this thing is a router. A router is sort of an intermediary node that usually connects to multiple neighbors. From a very different perspective, in this class, a router is often this. Sometimes it's this. We're probably not going to be 100% consistent, but it should be clear from the context. If you were to ask a network engineer what a router is, they might tell you that it's this. This is the schematic symbol that network engineers use to represent a router. Many of you, perhaps all of you, are familiar with this being a router, a home Wi-Fi router. This is also a router. This is a 24-port Cisco Catalyst. And this is a 96-port Cisco Catalyst. And so these two things are the kinds of things you might find somewhere in a campus network or maybe in a wiring closet somewhere. The previous one looks a lot like what a lot of what are called top-of-rack switches in data centers look like. And the big obvious distinction between these last two is the number of ports they have, right? Each of these little holes is a place where you can plug in a cable, or when we think about that logically, it's a place where a link can exist, right? So this one supports a lot more links than the previous one. Another note is that these last two in particular, a lot of people would tell you that these are a switch, but they do routing, so I'm going to say they are also a router. So again, the distinction between the two is not really all that clear. Another one, here's a thing called a Cisco CRS-1, and it's like it's called the carrier routing system. And this is the kind of thing that you might find in a major ISP. And so these things are big. This is, taller than I am. It can support many links, very high bandwidth links, and so on. So there are a lot of different kinds of actual routers. Again, in this class, to us, they're mostly just squares. So, any questions on those? So, moving on, we have this question like, why do we have routers at all? And maybe this ends up being obvious, but I thought we could sort of quickly just sort of think through a couple of the reasons. So, if you've got a couple hosts and you want to send data between them, it's pretty easy to just put a cable between them, and now A and B can directly communicate. If you've got more hosts, though, what are you going to do? You could sort of continue that same pattern and just put a link between every host, and now everybody can directly communicate with everybody else. So is there a problem with this? Yeah. It doesn't scale very well. Why not? Yeah, like every time you add something, there's a lot of work, right? Like there's a couple reasons you can think about why this doesn't scale, right? Like, for every host, like in the network, there's that many hosts minus one links that exist in that network, right? So, first of all, that doesn't probably scale to your home or your apartment, right? There's billions of devices on the internet. You probably don't have room for all the cable in your house. Also, anytime anybody added a new host, right, somebody would need to go to everybody's house and, hook up the new cable, right? So this obviously doesn't scale too well. And also, most of these links would probably be idle most of the time, right? Do you communicate with every single other host on the internet? Are there any positives to this sort of design, though? Yeah. Yeah, so connections are direct and low latency, and not just the latency, even more like the bandwidth, right? You've got dedicated bandwidth to everybody. So that's nice. Another thing is it's pretty robust, right? Like if this link between A and B fails, none of the other links are affected, right? All the other pairs of hosts can still communicate just fine. So if the scale is small and the need for your performance is great, this design might make sense. Another way you could think about doing it is something like this, where all the hosts are sharing like literally the same wire. So anything good or bad about this approach? Yeah.
Scales really well because all you have to do is add a little bit more wire to connect the host.
Yeah, so in some sense it scales really well, right? Like connecting a new host just means adding a little bit more wire. Anybody else? Anything good or bad about this approach? Yeah. Yeah, so in some sense it's not very robust, right? Like if this wire breaks anywhere, some of the hosts are going to get disconnected, potentially a lot. Any other thoughts, good or bad, about this approach? Yeah. Yeah, there could be a lot, like, as opposed to the other design where everybody had, sort of like reserved link to everybody else. Here, everybody is sharing the same link. Everybody's trying to fight for the same bandwidth. Right behind you? Did you have another? Same thing, okay. So, everybody's competing for the same bandwidth, maybe not very resistant to failures. We had one argument that it scales well because you could just add a little bit more wire to add another host. It also, you maybe would say, it doesn't scale to the size of the internet having just one giant wire that has to wrap around the Earth and visit every single person. So another good thing about it potentially is that maybe this is really cheap, right? It's just one wire. There's no extra nodes. There's no, forking of wires. So, again, there are cases where maybe this makes sense. Historically, a lot of local networks have worked like this. Ethernet traditionally worked like this. And so we may come back to this type of network a little bit in the future of this semester. But, here we can kind of see the benefits of adding intermediate nodes, these routers. First of all, you don't need an exponential number of links, right? You're also not trying to share a single link, so you've got sort of more bandwidth to go around. Like the traffic between A and C here doesn't affect the traffic between E and D at all. And if a link goes down, you may be able to find alternative paths. So this approach kind of solves some of those problems, and maybe you can see it as sort of like a nice middle ground. Any questions on this? All right, so now that we've talked about sort of the what and why of routers, let's start to dig into what I'll call the challenge of routing. So the basic challenge of routing is when a packet arrives at a router, how does the router know where to send it next such that it eventually gets to the intended destination? Like if A is trying to send a packet to B on this network, it's first going to arrive at this router R2. But should R2 send it to R1 or to R3? And when we make that sort of decision, we want to send the packets in a reasonable way, right? Using paths that are in some way good. And good could mean a lot of different things, depending on the context. It could mean the lowest price. It could mean the fastest. It could mean the most reliable. It could mean not using a competitor's network. In some examples on Thursday, we'll think of it as the fewest number of hops, in which case, a path like this between C and B, which would work, is not particularly good. And so this sort of takes some approaches off the board immediately. Like, imagine that routers know their neighboring hosts, but nothing else. So then what if a router, when it gets a packet, if the host isn't directly attached, what if it just forwarded it to another router at random, another neighboring router at random? Like, that would work, right? And it's really simple. And simple is good. But why wouldn't you want to implement routing that way? Yeah?